right, we're going to start talking about the definite integral. So this is the definite integral symbol. So we have the integral symbol. We have a to b of f(x) d of x. A is my lower limit of the integration. B is my upper limit of the integration. F of x is my function of the integrand, and d of x is my variable. So x would be my variable of integration. The integrability of continuous function, if a function f is continuous over the closed interval a to b, or if f has at most a finitely many jump discontinuities then the definite integral a to b of f of x d of x exists, and f is integrable over a to b. So that's just saying that if I know that it's continuous, I can integrate it. If I know where the jumps are and it's a finite number of jumps, I can still integrate it over those finite jumps, okay? But I would have to break it up into pieces of integration. So we have some rules of integration here. So if I have, if I'm integrating from a to b of f of x d of x, and I'm going to flip that. So I'm going to go b to a. That's going to be negative the integration of b to a of f of x. So if I flip my limits here, my upper and lower limits, it's just going to negate it. If I go from a to a of f of x d of x, that's going to give me 0. So if I'm going to integrate from a to b of k f of x dx, so I'm constant multiplier, I'm just going to pull that constant out front. So k times the integration of a to b of f of x d of x. Sum and difference. So if I have the sum and difference in the integral, a integrated to b of f of x plus or minus g of x d of x, I can break that up. So the integral of a to b of f of x d of x plus or minus the integral of a to b of g of x d of x. Now, if I go from a to b, the integral of a to b f of x d to x, and then I go from b to c of f of x d of x, I can actually combine those into the integral of a to c of f of x d of x. Now, if I have two functions, so if I have f of x is greater than g of x everywhere, and I integrate them, their integrals are going to be greater. So the integral of f of x is going to be greater than or equal to the integral of g of x. If I have a max and a min in my integral, the max from b to a times the max is going to be greater than or equal to the integral of f of x d of x, which is going to be greater than or equal to the minimum times b to a. Okay, so here we just have a couple of rules we're going to look at. So here I have the integration of negative 1 to 1 of f of x d of x is 5. And then I have the integration from 1 to 4 of f of x d of x equals negative 2. And we're going to apply these rules here. Okay, so now we have the integration 4 to 1 of f of x d of x. Well, that tells me that this is minus 1 to 4 of f of x d of x, which is going to be negative 2, which gives me 2. Okay, so if I'm going from 4 to 1, kind of going backwards, I get the negation of this, which is 2. So now I'm going from negative 1 to 4. Well, what this is looking at is this is saying this is negative 1 to 1 of f of x d of x plus 1 to 4 of f of x d of x. So now I have from here, negative 1 to 1 is 5 plus negative 2, which is 3. There's my answer. Okay? So a lot of this is just kind of getting those rules. We're not actually taking the antiderivative yet and finding those. Okay? We're going to do that in the next section. If y equals f of x is a non-negative integral over a to b, then the area under the curve, y equals f of x over the closed interval a to b is the area equals the integral of a to b f of x d of x. This is, last time we talked about using rectangles, and this is kind of where Riemann sums comes in, the more we take it. We are going to look at this area as being the integration from a to b of f of x d of x. Very important to understand that that's our area formula. Our average value formula, if f is integral on a to b then its average value, or the mean on a to b, is equal to 1 over b minus a, the integral of a to b f of x d of x. So this is just kind of a touching base on some of these rules of integration. We haven't actually talked about what happens, what do I need here when I do this. We're still in the integral. We haven't taken the antiderivative yet and plug values in. That comes next time.